check your understanding. We have two stars, A and B, with the same temperature, but star A has twice the radius of star B. Twice the radius means the area now, because the area is pi r squared. If you square the radius, then the area would be quadrupled. What is the ratio of star A's power output to star B output due to electromagnetic radiation? We are told the emissivity of both stars can be assumed 1. So here in this case, I think it's clear. The answer would be 4, because you are dealing not with R, but dealing with the square of R when you check the area. So the ratio between the power of A to the power of B is 4 times, because the radius of A is 2 times the radius of star B. Another problem. Star A has twice the absolute temperature of star B, but they both have the same radius. So now you are talking about the factor of temperature. What is the ratio of stars A power output to stars B output due to electromagnetic radiation? 4, 8, 16, or 64?
Would it be 16?
Any suggestion?
Can you hear me?
Okay. The answer is 16. From Stephen's law, the power is equal to sigma A E T to the power 4. So when the temperature of A is twice the temperature of B, you have 2 to the power 4. 2 to the power 4 is 16. So the power from star A is 16 times the power from star B. Another situation, star A has twice the absolute temperature and twice the radius of star B. So now you have the factor of the temperature and the factor of the area. What is the ratio of stars A power output to stars B output due to electromagnetic radiation? Any suggestion?
Can you hear me? Can you hear me?
Okay, it is 64, because now twice the radius, twice the temperature. The factor 2 here squared will give us 4. The factor 2 here to the power 4 will give us 16. 4 by 16 is 64. We move on to another application, which is the Dewar flask, when we talk about the thermal processes. This is widely used to keep the thing, if it's hot, to stay hot, or if it's cold, to stay cold. So the Dewar flask is manufactured with a good insulating jacket here and silvered surfaces to reflect, so it will not absorb or emit radiations. It will keep its own heat energy. There is a vacuum area here to improve the insulation. We need to minimize the heat transfers in or out. So the design is usually to minimize the energy transfer by conduction or convection or radiation. Another application is the greenhouse. We are all familiar with the greenhouses, as you can see here. During the daytime, the sun rays will penetrate the glass and deliver energy. It will be absorbed by the walls, by the soil, by the plants. So the energy from the sun will be absorbed. But once it is absorbed, now the various entities inside the greenhouse can re-emit the energy. They emit it in the form of infrared. The infrared will cause the temperature here to rise inside the greenhouse. But infrared cannot escape from glass. Cannot escape from glass. So in theory, all the energy that was received during the daytime will be trapped inside. Of course, there is energy through conduction to the ground, for example, energy transfer through conduction, okay? But through radiation, it cannot penetrate glass. The infrared will be trapped inside. This is the greenhouse effect. It applies also to Earth. Earth, there is energy absorption, there is energy emission. In the ideal situation, we want the energy emission and energy absorption to be the same, to have balance between them, to have equilibrium.
Hey, Mr.
But because
Al-Kofahi.
of the carbon dioxide released from human activities, like power plants, fossil fuels, cars, automobiles, etc., because of the carbon dioxide, which is the rate 3.5 by 10 to the power 10 tons, okay, to the atmosphere, the energy from the sun rays will be trapped, and this way the balance is disturbed, and the whole earth now is like a greenhouse here. So ideally, we need to control the release of carbon dioxide, to limit the release of carbon dioxide in order to fight that greenhouse effect and to restore the balance in our ecosystem. We covered most topics in this chapter. A few questions to check our understanding. Which of the following phrases best describes heat? Heat is the total energy flowing between two bodies at different temperatures. This is the best description for heat, okay? Then two objects made from the same material have different masses and different initial temperatures as shown. If the bodies are placed in thermal contact, the final equilibrium temperature is most nearly to be. So you are talking different masses and different temperature. This leads us, in order to solve this problem, to introduce a new quantity which we call the heat capacity. Not specific heat, heat capacity. Heat capacity is equal to the product of the specific heat by the mass. So in order to do the comparison, you need to multiply specific heat by the mass. In other words, you are comparing the heat capacity. In this case, most likely 47 degrees will be the equilibrium temperature. Two identical thermodynamic systems, one at temperature T1, the other at temperature T2, are placed in thermal contact. So we are talking about identical thermodynamic systems, but at different temperatures. When they reach thermal equilibrium, what is true about the final temperature? Any suggestion? So because they are identical, then the final temperature will be just the average, half T1 plus T2. By what factor would the total power from a black body be modified if the surface area were to decrease by a factor of 2 while the temperature was doubled? So we need in this case to use this Stephan law for the energy transfer by radiation, and the answer is 8. In this chapter, we learned about thermal processes. We learned how the heat is absorbed and used to raise the temperature. If the heat is released, then it will lower the temperature of the substance. We also learned about phase transformation, when the substance stays at the same temperature but changes the phase from solid to liquid, or from liquid to solid, from liquid to vapor, or from vapor to liquid, and so on and so forth. When we solve the problems there, we apply energy conservation. The total change in the energy is zero. That is to say, the energy loss is equal to the energy gained. Usually in any calorimetry process, there will be items that are gaining energy and items that are losing energies, and we use these two formulas to calculate the quantity of heat energy. We also learned about heat transfer by conduction, and in that case, it depends. The heat transfer by conduction depends on the difference between the hot end and the cold end. It also depends on the length of the path, the thickness of the wall, for example. It depends on the area and on the type of the material, K. Then for heat transfer by radiation, there's absorption and emission, so we need to take both into consideration and to apply Stephen's law in order to solve. And there we need to be careful that T needs to be in Kelvin.